Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Greetings everyone. Welcome to the continuation of the control systems lecture for the course SMJE 3153. So in this video I will talk about a new topic called steady state error. So I would like to welcome back all of you from the mid-semester break. I'm sure you are well rested. So in this video I will first of all review several important concepts that you have covered before getting into the topic of steady state errors. So in particular I will talk about all these definitions, modeling, block diagram and so on, all the way up to stability that you have covered before. Okay, in the introduction of control systems, you should have been given the overall picture of a control systems, easily done by using a block diagram. So you should have understood the concept of a block diagram, and the important terms related to the block diagrams and in general to control systems should have been given to you. I've listed down some of them here. You know, the input, output, control variable, set point, and so on. So make sure you have understood this terminology very well by now, because I will be referring to this some of this later on. Next is the topic of modeling. I think you have spent a lot of time trying to obtain the mathematical model of a real physical systems. You should have looked at electrical, mechanical, electromechanical systems, and maybe water level systems, and trying to obtain the mathematical representations. And normally you will start with obtaining the differential equations in the time domain, and then transforming that equation using Laplace transform into the frequency domain or Laplace domain, as shown here. Although in some cases in the time domain equations you would have in some physical system linearity, non-linearity presence. So this can be linearized, the non-linearity can be linearized first, and then you can apply the Laplace transform to obtain the equations in the frequency domain. And in the frequency domain you would have obtained the block diagram representation and analysis like poles and zeros and so on. So this is an example of the of the RLC circuit, where the mathematical representation in the frequency domain can be just written down by inspection. I think you can do that by now. And if you have defined the input to be V, so if this is the input voltage and the output is the current, so you can represent the V in the denominator and I in the numerator, and you can rearrange this equation into this form, and this is actually the term transfer function and can be represented using a block diagram where the input is V and the output is I. And once you have the block diagram, the idea of poles and zeros comes into play. So you can find the zeros, which is 1 0 at the origin, and there should be two poles, and I've plotted the pole zero map using MATLAB here, and you can see there are two poles here, 1 0 at the origin. And the idea of stability initially simply said if you have all the poles in the left half plane, then you would have a stable system. So make sure you know how to plot this quickly in MATLAB. And if you don't have MATLAB, you can also install other softwares. So for example, Scilab, these are open source. This would help you in the assignment or maybe in the test and exam later on. In the topic of time response, you should have looked at the first and second order systems, and because these are the typical systems occurring most of the time in real life. And in particular for the first order system, you can model it using the first order plus date time as shown here, where you have the gain k, the time constant tau, and the date time theta. So just three parameters to represent the first order with date time. And when you have a stable system, this is the response of 1 over s plus 1 as shown here. So you can calculate the rise time and the settling time. For second order systems, there are more parameters, of course, where you have the natural frequency, omega n, damping ratio, gain, k, and date time. And for the second order response parameters, as shown here in the red, that's the critically damped. The yellow one here is underdamped, and this is the undamped response. And you can plot the second order response and obtain the typical parameters consisting of the overshoot, the peak time, rise time, and settling time. So these are the, you should know how to simulate simple systems using Simulink and to obtain the response as shown here. And also, by the way, you should be able to obtain the from the equation how to sketch the curve, and also if you are given the curve, how to obtain the transfer function. So just from this, for example, the first order response here, can you give me the equation representing this curve? So you can see this is a first order response. So by calculating the settling time, rise time, you can obtain the time constant, the gain, and the theta if you know the input. In this case, the input is the step response. Next is the block diagram simplification topic, where in reality you don't have just one block representing the overall systems. You may have a big system and you have several blocks, and how to simplify the block to obtain the overall transfer function. I think the idea of block diagram simplification, or if you want to represent your control system using the signal flow graph, is the same thing. And also there's a Mason's rule that you can use to simplify the block diagram or the signal flow graph. Next is the topic of stability. So I'm sure you know that in general the poles should be in the left half plane, but in some cases, like for example in this case, it's not really clear what will be the poles of the system. So the idea of Routh-Hurwitz criterion allows you to just using the coefficients of the denominator of the closed loop system, and just by using the Routh-Hurwitz process, you can identify if there are any poles in the right half plane which cause the instability just by looking at the sign changes. Okay, I think that has also been covered by Dr. Fitri. So in this case, I'm plotting this system. Although in the open loop it's stable, but if you apply the closed loop here, in the unity feedback, negative feedback system, then you can see that there are like two sign changes here and causing the system to be unstable. Okay, so the topic for today is actually steady state errors. So we have covered the transient part of the response. We are looking at the steady state part of the response now. So here, the definition for steady state error is the difference between the input and the output of a stable system. So make sure the system is stable first, for a prescribed test input as t approaches infinity. So by definition, it's easier to look at in this first block diagram where you have a closed loop system. The output is C and the input is RS, and the difference will be E. However, in general, most of the time we will look at the unity feedback system as shown here, negative feedback system, where the input R and output is C, and the error can be easily obtained naturally in the setup of the system, where E is just R minus C, which is the same here. And for example, I've plotted this response of a negative feedback unity feedback system, and you can see that the steady state in the steady state, you can see that there are errors occurring consistently. In the first case, when you have a step input, then the error is constant. Okay, at every time instant there is a constant error. Whereas in the second case, when you input the RAM to the same system, you can see that at each time instant that the difference between the green and the red increasing as time goes by. So this is an example where the steady state error is infinity, whereas this is an example where the steady state error is a constant. So both are undesirable. We want as much as possible that the steady state error should be as small as possible or zero if possible. Okay, let's look at the steady state error for the unity feedback systems in more detail. So this is the block diagram as shown before. So let's analyze the equations. E is equals to R minus C as shown here. But we also know that C is E times GS. So if you substitute ES, GS back into the original equation, then you can solve for the expression for the error. Okay, so ES is equals to RS over 1 plus GS. So the procedure to find ES is, number one, is you need to check for closed loop stability. So regardless of these equations, you have to use some methods to identify that the system is firstly stable in the closed loop sense. And then once you have you can use Routh-Hurwitz, for example. Okay. So and then you can use the final value theorem. So just a review in the Laplace theory, the expression for this E at infinity, this is in time domain, is equals to the limit as S approaches 0, S times ES, this is in the Laplace domain. So this equation ES, if you multiply it by S, so S RS over 1 plus GS, if you find S is approaches 0, then you can obtain the E at infinity. That is what we want to know for a particular system. So for example, in this case, we will look at the case when the input is a step input. So for a step input, you can apply Laplace transform to the step input to obtain Rs is equals to 1 over S. So if you substitute 1 over S back into the equation before, and you apply the final value theorem, then you will see that in order to get E at infinity, or the steady state error equals to 0, then this expression must be infinity. So for this expression to be infinity, then GS must have this following form, where n must be 1 or must be larger than or equal to 1, so that if you have one remaining S here and you substitute S equals to 0, then the whole expression here will be very infinitely big, because you are dividing by 0. So this will be infinity, and the whole expression will be 0. That is what you want. So in this case, I've added an integrator. If you go back to the original model, it's just S plus 2. So now I've added an extra S, which is an integrator. And you can see that in the case for the input is a step, then the steady state error is now 0 as predicted here. However, when we have a ramp, there is still remaining the steady state error of a constant. So now it's no longer at infinity. Before, when we don't have the integrator, the steady state error here is infinity, but now it's a constant, so much better than before. But this is much better for the case of the step input. The steady state error is now 0. So next, let's look at what happens when we have a RAM input. So we apply the Laplace transform to the expression for a RAM input. In the time domain is t times ut. So if you apply the Laplace transform in the Laplace domain is 1 over s squared. So you substitute 1 over s squared in the expression for the steady state error, and you do some analysis, and you will see that in order for the steady state error equals to 0, then this must be infinity, where the limit in the denominator must be infinity. So we need to have the limit as s approaches 0 of this expression equals to infinity. So in this case, it's the same expression as equation is the same equation 2 before, but you need to have that the system must have n, not 1 anymore, it should be 2 or more. So in this case, I've added another integrator to the system. So the denominator becomes s cubed. Before it was s squared. Previously it was just s. So now it's s cubed plus 2s squared. Okay. And you can see that the response of the system during the step input has 0 steady state error. And what's nice about this is also that in the case of the RAM input, it also has the 0 steady state error. So the step and the RAM, and there's another one, parabolic input. These are the standard test vector, test input used to normally used to test control systems. The step are normally used to test for position, okay, systems. The RAM for velocity, whereas the parabolic for acceleration. So it depends on the systems that you are testing. I would like to note here that if you notice that previously the numerator is just a constant, okay, you can see that I've added a 0 here. The reason is, well, you cannot just easily add an integrator. In this case, if you just add an integrator, then the whole system becomes unstable. So you can adjust the numerator to ensure that the closed loop system is stable. So in this case, I've added 2s plus 1. If you recall in the previous slide, it's just 2. Okay, it's just 2. Finally, we will look at the error with parabolic input. So if you transform the expression for the parabolic input, you will get Rs is equals to 2 over s cubed. And if you substitute 2 over s cubed into the same equation, you will see that in order for the steady state error to be 0, then you need to have the denominator here to be infinity, and in this case, same as before, equation is the same, but in this case, because you have extra s squared here, then n should be 3 or larger. So you need to have s equals to 3 or more. In order that you have a division by 0 here, causing gs to be very big as s approaches 0, in which case you will have the steady state error equals to 0. So in this case, you can see that this is the same, this is the system before, the system shown before, where for the RAM it has 0 steady state error, but if you just use it here, you can see that there's constant error for the case of the parabolic input. But if you add another integrator here, okay, in this case I've added another s, so the denominator becomes s to the power of 4 plus 2s cubed, then you can see that the steady state error for a parabolic input is 0 as predicted here. What's nice about, okay, think about this, I would like you to do this before class. Think about what will be the expression, because if you just add another integrator here, then if you don't change the numerator, then the closed loop system will be unstable. So if I were to add this another integrator becoming s4 plus 2s cubed, what will be the expression for the numerator to cause the system to be stable? So you can do that at home, and we will discuss this in class later on. But try to do this first before before I give you the answer later on. But as a hint, you can just write an expression for the numerator having one or two parameters where the parameters are unknown, and you can use the Routh-Hurwitz in the closed loop system and try to find those parameters that will cause the system to be stable. So that is one of the way to find this unknown numerator. So please try to do that at home. Okay, finally for today, as an example, so assuming you have this system 100 s plus 2s, so you have 2 zeros and 3 poles here. So find the steady state error for inputs 5 ut, that's the unit step, and then the ramp, and then the parabolic to the system shown here. So first we need to check for the stability of the closed loop system. So you need to use the knowledge that you have learned before when you learn Routh-Hurwitz, or maybe you cannot just directly use the poles and zeros here, because you need to obtain the closed loop system first and then find the poles. So if you do that, then the closed loop system is given here. You can check that, and the stability can be checked using Routh-Hurwitz, and essentially you will get these poles. So you can check using Routh-Hurwitz. Essentially they are stable because all of these are in the left half of the complex plane. So once you have identified that the system is stable, so you just use the equation 1, the expression for the steady state error, substitute the expression for the input. Okay, so for the case of the step, you would have 0 steady state error. For the case of the ramp, you would have 5 over 100, so that's a constant. And for the case of the parabolic, you can just guess the GS has s to the power of 1, so here it should be constant and here should be infinity. Okay, infinity as predicted from the equations before. Okay, so thank you for your attention. I hope you have understood most of what has been presented in this video. Try to answer the short quiz. The link is provided in the description of this video below. And so until the next class, I'll see you. Bye bye. Assalamualaikum warahmatullahi wabarakatuh.